Hello viewers, welcome back to my channel Experience Physics, and for today's lecture we are taking the topic temperature dependence of resistivity. Resistivity or resistance? Resistivity or resistance? Temperature dependence of resistivity, right? The question is, does the resistance or resistivity change with respect to temperature? Yes, the answer is yes. But in most of the experiments, we are used to assume that it is constant. But in practice, it is not so. The temperature is affecting the value of resistance as well as resistivity. This is the subject of today's lecture. Let me start from writing the expression for resistance. R is equal to M upon N E square tau L by. This is actually obtained from the current equation, right? I is equal to ENA VD. We know ENA, I am replacing VD, drift velocity, with its expression EE by M into tau. Then again, I am replacing the E with V by L. E by M, E is replaced as V by L, right? Then this will be N E square tau by M L by A into V. This is I. Then V by I is equal to M upon, actually this is A by L, right? M upon N E square tau L by A. This is R. M upon N E square tau L by A. So the entire expression has been done in a separate video under the title Origin of Resistivity. The link for that video is also given in the description box. If you have not watched that video, please go and watch it, right? The entire expression and its relevant discussion is made in that video. R is equal to M upon N E square tau into L by A. M constant, right? I am coming here. M constant, mass of electron, N free electron density, then E charge on the electron, tau average relaxation time, L length of the conductor, A cross sectional area of the conductor. This length of the conductor and cross sectional area of the conductor are in our control, the user's control. I can have any length. Similarly, I can have any area of cross section, right? So these are the shape of the material. These depend upon the shape of the material. But M, I can't change. Similarly, N, if the material is chosen, N is constant. E, charge of the electron, tau relaxation time. All this, if you keep the temperature, tau is also constant. This is also discussed in the previous video. So M, N, E, tau, everything is constant if you keep the temperature constant. So we can make it as this M upon N E square tau as rho L by A. So this is resistance and this is resistivity. You can make R is equal to rho if you keep L and A as 1 and 1 meter and 1 meter square, that's fine, right? So let me take again this expression. R is equal to M N E square tau L by A. I will write it as R is proportional to M N E square tau. First I have limited L and A as constant. L and A, the chosen material. This is a chosen resistance, right? Length I know, cross-sectional area I know. So R is proportional to M upon N E square tau only. M always constant, mass of electron. N free electron density. It varies material to material, right? Our topic is temperature dependence of resistivity. The temperature dependence of resistivity varies material to material, right? E always constant. M we know the value is 9.1 into 10 to the power of minus 31 kg. E charge of electron 1.6 into 10 to the power of minus 19 coulomb. These numbers are fixed, right? So M and N M and E are going to be these numbers. Then I have this expression R is proportional to 1 upon N into tau. R is proportional to 1 upon N into tau only. So this is the expression we are going to use to discuss about the temperature dependence of resistivity or resistance, right? Okay. R is proportional to 1 upon N into tau, because N is going to vary with respect to the material, chosen material. Copper, it has different value. For example, for copper, N is equal to 8.4 into 10 to the power of 28 electrons per unit volume, that is per meter cube. Aluminium, the value is 6 into 10 to the power of 28 electrons per meter cube. Free electrons per meter cube, in fact. Free electrons per meter cube. So material to material, N is going to vary. Tau average relaxation time. What we have discussed about tau in the previous video, under heading drift velocity, we have discussed in length the tau. Average relaxation time, the time interval between two successive collisions of an electron, right? An electron comes here, first collision, then second collision. How much time it is taking? This is our electron. First collision and second collision. Average time interval between two successive collisions. So this is relaxation time, right? So this is also going to change material to material, right? So let us discuss the entire concept here. Before discussing the concepts of temperature dependence of resistivity, I am going to group the entire material which are in use into three categories, right? Three categories I am going to distribute all the materials which are available in practice. Number one, metallic conductor or simply metals. Number two, insulators. Number three, alloys, right? We will see them. Number one, metals or metallic conductors. R is proportional to 1 by N into tau. R is proportional to 1 by N into tau. N free electron density in metals, N value is very high. In metals, N value is very high, right? The high value of free electrons, they move very fast because temperature is going to vary. We are discussing the temperature dependence of resistivity. We assume the temperature is increasing. Let us assume the temperature is increasing. If the temperature increases, all the free electrons will have more kinetic energy. They will move fast. they will quickly collide with the positive ions. The collision will happen frequently, right? Frequently means we have this relation. Whenever you see the word frequency, 1 by t will come. In this case, it is tau, relaxation time. Quickly they are colliding, immediately, very fast. The collision happens very, very fast, right? So relaxation time will reduce. In metals, n is very high, n is small. Or otherwise I can write tau decreases, n increases. N increases because temperature is increasing. We assume temperature is increasing. The increased temperature makes more free electrons. More free electrons means more number of free electrons are passing through the entire material. They collide with the positive ions. The collision happens frequently, right? So n increases, tau decreases, right? So R is proportional to 1 by, so 1 is increasing, another is decreasing. Two opposite actions happen. N is increasing, tau is decreasing. So we will assume or we will understand that one increase is compensated by one decrease. So R has to be constant. No. Because metals, already metals having the order of 10 to the power of 28 free electrons per meter cube. So this much of electrons are available, free electrons. So due to the temperature, the addition of some more electrons may not give an appreciable increase, right? Already there are a large number of electrons. Addition of some more few electrons will not give an appreciable amount, right? So the increase in n is negligible here. It is negligible here. Already there are a large number of electrons. So R is proportional to 1 by tau. So this increase is neglected. R is proportional to 1 by tau. Tau decreases. R increases. So T increases makes tau decreases, R increases. Where? In metals. In the case of metals. In the case of metals, if you increase the temperature, relaxation time decreases or increases. So that is the conclusion. If we draw the variation, I will take R or rho. So resistance has resistivity. Here the temperature in Kelvin. T increases, R increases. T increases, R increases, right? So the shape of the curve like a parabola. The shape of the curve will look like this one for metals. Clear? So in metals, so this one, after making M and E constants, I am writing R is proportional to N by N into tau. Free electron density, it is not giving any appreciable increase. So we are writing R is proportional to tau, 1 by tau only. Tau decreases because of the increase in temperature. So resistance increases. Simple. Second case, alloys. So combination of two or more material, alloys. For example, nichrome, nickel and chromium, manganese. These are some of the alloys. Constantan, metallic alloys, right? R is proposal to, again I am writing N into tau. Let us see what is happening to N and what is happening to tau. So here, these alloys, in alloys, the free electron density is very, very high. That means you cannot neglect it. In the case of materials, we simply neglected it because it is not giving any appreciable amount. But here you cannot neglect it. In alloy, it is very, very high. N cannot be neglected. So both N and tau are acting. N is increasing, tau is decreasing. The increase in N is compensated by decrease in tau. The increase in N is compensated by the decrease in tau. But still, the tau will dominate N. Still, tau dominates N. That means it is not taking place in equal proportion. 10%, 10%, no. This is 8%, this is 10%. That is the domination. The decrease may be 10%, the increase in N may be 8%. This is slightly lesser than the changes. The change is slightly lesser than the change in tau, right? So it is dominating. Which one? Tau is dominating. That means it is decreasing overall. It is a constant line, near constant line, not a constant line. If the increase and decrease are happening in equal proportion, we will get this perfect horizontal line. This is R as well as rho. This is temperature. Perfect horizontal line. This is increasing. This is 10% increasing. This is 10% decreasing equally, but not here. In practice, the decrease in tau will be more than the increase in the N value. So we can't get an exact horizontal line. We will get a line like this. Yes. Almost flat, but not flat. Almost flat, but not flat. So that is why in most of the electrical experiments or electrical appliances, this material is used. Potentiometer, bridges, rheostats. In the laboratory, you would have seen that rheostats. To change the value of resistance using the slider, you would have done those experiments. So these are the nichrome wire. On the rheostat, you may see the nichrome wire wound over it, right, in iron boxes. So these are some of the appliances, electrical appliances. The metallic alloys are used, right. So this is the characteristics or variation of resistance or resistivity with respect to temperature in the case of alloys, right. So third one, semiconductors and insulators. Semiconductors and insulators. Semiconductors are not insulators, but both the materials are behaving in the same way as far as temperature is concerned. That is why I have grouped, or we have grouped, the semiconductors and insulators and put them in a single group. Right? R is proportional to 1 by tau. The temperature variation highly affects semiconductors. How? At low temperature, N value is less. At high temperature, N value is high. At low temperature, N value is less. At high temperature, N value is high. So that means at low temperature, tau dominates. At high temperature, N dominates. Right? So if we draw the graph, this will be 0. This is temperature, or I will write it as low temperature. This is high temperature. This is R or rho. So at low temperature, it will possess high resistance. When you increase the temperature, it will possess low resistance. So this is the behavior of semiconductors or insulators. Both semiconductors and insulators are giving this shape of the characteristics, R versus temperature, right? So in metals, in alloys, and in semiconductors, yes. Please remember the shape of the curves. In metals, it is increasing. In alloys, it is almost flat, not flat. But still it is slightly increasing because tau dominates N. Here it is decreasing. In the case of semiconductor, it is the opposite action of conductors, right? You can remember this way. So the opposite action of conductor will do the insulator. This is increasing, this is decreasing. Right? Okay. Now let us quantify the temperature variation with respect to resistance. Resistance, I have given one resistance. I have taken one resistance. How the temperature is affecting the resistance? Let us see. The change in resistance let me take it as dr, change in resistance. Similarly, change in temperature dt. Initial value of temperature, initial value of resistance. Initial value or reference value, RO. Final value, RT, for any temperature, right? From the reference value for any temperature. And the initial temperature is TO. Final temperature is, let it be T. Reference value and any temperature value of your wish, right? dr is proportional to dt. So we have discussed here. dr is proportional to dt. dr is also proportional to RO, the reference value, initial resistance value. If the initial resistance value is more, the difference will be more. The temperature variation, due to temperature variation, the change will be more. If the initial RO is less, this also be less, right? Small variation for small initial value, high variation for high initial value, right? So I will group them. I am going to group the two things. dr is proportional to rho dt. Then dr I am making is as is equality sign is equal to one constant. That constant is known as alpha or written as alpha rho dt. This is known as temperature coefficient of temperature coefficient of resistance. Alpha is called as temperature coefficient of resistance. For copper, it has one value. For aluminum, for iron, for alloy, material to material, different alphas will be there. Experimental values are available in the data sheet, right? So dr is equal to alpha rho dt. I am going to integrate both sides. Alpha constant, material constant. Initial value, this is also constant. Only the change is temperature. Integrate temperature only. Initial value, this is rho. Final value, this RT. Yes, RT. Initial value TO, final value any temperature, right? So this will be R, the limits are RO RT is equal to alpha RO, this is temperature, the limits are TO T. Then putting the limits, RT minus RO is equal to alpha RO T minus TO. I want RT, the resistance value at any temperature, that is final temperature, is equal to RO plus alpha RO T minus TO. So RO can be made as common. So this is 1 plus alpha T minus TO. So this is the final expression. Resistance for any temperature RT is equal to RO, initial temperature of 1 plus alpha T minus TO. This T minus TO will also be written as delta T in simple. So RT is equal to RO 1 plus alpha delta T. So this is the expression what we can use to know the the resistance for any temperature rise, right? This is a change in temperature, alpha material constant, temperature coefficient of resistances, initial value. If you know the three values, you will get the resistance value for any temperature, right? Clear? Right. So this is how we are quantifying the change in resistance, right? Using this expression, we can find the resistance value for any temperature rise, right? Yes. So these are few problems we can solve here. So for metals, R versus T. For alloys, R versus T. For semiconductors, R versus T. So these are the three graphs. Then RT is equal to RO of 1 plus alpha delta T. Delta T is T minus T, change in temperature, right? So this is what we have discussed so far, right? Using this concept, let us try to solve few problems. Right. The first one, two different conductors have same resistance at 0 degrees Celsius. It is found that the resistance of the first conductor at T1 degree Celsius is equal to the resistance of the second conductor at T2 degree Celsius. The ratio of the temperature coefficients of the resistance of the conductors alpha 1 by alpha 2 is what? Right? Two different conductors, same resistance at 0 degrees Celsius. So we will use alphas are asked, the ratio of alphas are asked. Let us use this expression, RT. Instead of T, let me write R1 for first conductors. So R1 is equal to RO of 1 plus alpha delta T. R2 is equal to RO of 1, this is alpha 1 delta T. The change in temperature also given, T1 degree, and this is for T2 degree Celsius. Right. Alpha 1 of T1 minus 0. Initial value is 0 degree Celsius. This is delta T. Alpha of T2 minus 0. Yes, right. R1 and R2 are equal when the temperature are T1 and T2. The resistance of the first conductor at T1 degree Celsius is R1. The resistance of the second conductor at T2 degree Celsius is R2. Yes, I have put T1 here, then it is R1. Then T2 here, then we can make R1 is equal to R2. Yes. If we equate these two expressions, we will get one of the answers which are given in the options. Right. First, let us remove RO. R1 by R2 is equal to RO of 1 plus alpha 1 T1 divided by RO of 1 plus alpha 2 T2. RO cancel. Right. Now R1 is equal to R2 when it is T1, when it is T2. That means 1 plus alpha 1 T1 is equal to 1 plus alpha 2 T2. 1 and 1 can be cancelled. Alpha 1 T1 is equal to alpha 2 T2. Alpha 1 by alpha 2. T2 by T1. This is the answer. T2 by T1. Option D. Alpha 1 T1 is equal to alpha 2 T2. Yes. T2 by T1. Yes, simple. Next one. A silver wire has resistance of 2.1 ohms at 27 degrees Celsius and a resistance of 2.7 ohms at 100 degrees Celsius. When temperature is changing, resistance is changing. Determine the temperature coefficient alpha. Alpha is how much? Right. 2.1 ohms at 27 degrees Celsius. 2.7 ohms at 100 degrees Celsius. When it is changed to this much, resistance is changing. The question is to find alpha. We'll write the general expression RT is equal to RO of 1 plus alpha delta T. RT is equal to RO plus RO alpha delta T. Delta T is change in temperature. 100 minus 27 is the delta T, right? we want alpha. Alpha is equal to RT minus RO divided by RO into delta T. So here delta T is 100 minus 27. RT is given 2.7, RO 2.1, right? We'll put all the values here. RT 2.7 minus RO 2.1 divided by RO 2.1 into 100 minus 27. Which will be, this is 0.6, this is 2.1 into 73, 0.6 divided by 2.1 into 73, 73 into 2.1, this is 2 into 73, 146, the 0.1 into 73, 7.3, this will be 153.3. So this is 153.3. Let me write 0.6 as 6 into 10 to the power of minus 1 divided by 153.3. Or I can write 3 digit I want. Yes, let it be 600 into 10 to the power of minus 3. I am making it as 600 into 10 to the power of minus 3, right? This 153.3, I can approximate it as 150. 153.3, assume it as 150, right? So that we can easily do it. The calculation we can easily do it. Then we will find the closest value to the given options, right? Now 150 into 600 is 4. 150 into 600. So the answer will be 4 into 10 to the power of minus 3. This is approximate answer. Approximate answer is 4 into 10 to the power of minus 3. Let us find the closest answer to the approximate answer. 3.9 is coming closer to 4. 5.5, no. 8.8, it is far away. And this is 1, this is low value. So the answer is 3.9 into 10 to the power of minus 3. Just I am approximating and I am making the calculation quicker, right? This is a general formula. From this formula we can solve any type of problems if temperature, if resistance is asked, right? At what temperature will the resistance of a metal wire becomes 3 times its value at 0 degree Celsius? Temperature coefficient of resistance of copper is given. That is alpha is equal to 4 into 10 to the power of minus 3 per degree Celsius. At what temperature will the resistance of a metal wire becomes 3 times more? Initial value is RO, final value is 3 times of initial value. This is what given here. At what temperature? T is what? The question is. So we will start from the expression RT is equal to RO of 1 plus alpha delta T. First I will write delta T. From this we will separate T. Right. RT is 3 RO. 3 RO. This is RO. RO can be removed. 3 is equal to 1 plus alpha delta T. So alpha we can write 4 into 10 to the power of minus 3, it is given. So 3 minus 1. This is 3 minus 1 is equal to alpha delta T, and 2 is equal to alpha value, we can write 4 into 10 to the power minus 3 into delta T. So delta T is equal to 2 divided by 4 into 10 to the power minus 3, which is 1 by 2 into 10 to the power 3. This is 0.5 into 10 to the power 3. The options are 500 degrees, yes, 500 degrees Celsius. 0.5 into 10 to the power 3. 400, 300, 200, 500. So 3 times more than the resistance of the initial value. That is the hint, right? The voltage V versus current I graph for a conductor at two different temperatures T1 and T2 are shown in figure. The relationship between T1 and T2 is what? V versus I. So for T1 the graph goes this way, for T2 this graph goes this way. The question is what relations they are making, T1 and T2. Ratio V by I is equal to what? R. According to Ohm's law, V by I is equal to R. So V by I, so the slope is equal to R. Slope is nothing but R. For T1, the slope is more. So more R. More slope, high R. This is low R because this is less slope. For T2, this is less slope. This is more slope. More slope means high resistance, low resistance. T is directly proportional to R because it is conductor. For conductor, T increases, R increases. Right? If it is insulator, it is different case. But it is conductor. So this graph will be suited. So more slope means high R. Less slope means low R. Right? So but T1 is greater than T2. T1 is greater than T2. Option A. T1 is equal to T2. T1 is less than T2. T1, T2 are 1. Wrong. Resistance of a metal wire at 27 degrees Celsius is 4 ohms. If its temperature coefficient is 15 into 10 to the power minus 4 per degree Celsius, the approximate temperature at which its resistance becomes 6 ohms is resistance of a metal wire at 27 4 ohms at 27 degrees Celsius. Temperature coefficient is 15 into 10 to the power minus 4 per degree Celsius. The approximate temperature at which the resistance becomes 6 ohms is 6 ohms. It is becoming 6 ohms. At what temperature? At what temperature the 4 ohm is becoming 6 ohms? Initially it is 27. Alpha is given. Simple. Straight away you can use the formula and we can find the answer. RT is equal to RO of 1 plus alpha delta T. We want temperature. Right? First I am expanding RO plus RO alpha delta T. We want temperature. Right? Delta T is equal to RT minus RO divided by RO alpha. RT available, RO available, alpha available. RT, final value 6 ohms, minus 4, RO4, alpha 15 into 10 to the power minus 4. This is 2. Divided by 4 into 15. 10 to the power minus 4, let me write here. So this is 2. So this will be 10 to the power of 4 divided by 2 into 15, 30. 1 0 I can remove. So this is 10 to the power of 3 by 3. 10 to the power of 3 means 1000. So this is 333.33. Delta T. Delta T is T minus TO. Delta T is T minus TO. Final value minus initial value. TO, it is 27 degrees Celsius. Initial value. So T is equal to 333.33 plus TO, which is 27. 27 plus 33 is 60. .33 is the answer. Yes. 360.33. 273, no. 567. This is 475. This one. Again, voltage current relationships, T1 and T2. We have to take the slope. High slope means high resistance. Just a while before we have seen one problem. The voltage current for a conductor at two different temperatures, T1 and T2, are shown. R1 and R2 are resistances of the conductors at T1 and T2. Here the resistance is R1, here the resistance is R2. They are given. The correct relation between R1 and R2. R1 is equal to 3 R2, R1 is equal to R2, R2 is equal to 3 R1, R2 is equal to root 3 R1. Again we have to find the slope and make the relationship between R1 and R2. Right? The angle is given. So for the slope, tan angle for T1 or R1, for R1, if it is 30, then this will be 60 degree. I will write tan 60. For R1, tan 60 is equal to root 3. R2, tan 30, this is R2. 1 by root 3. R1 by R2 is equal to root 3 upon 1 divided by root 3, which is equal to root 3 into root 3. So this is 3. R1 by R2 is equal to 3. That is the answer. So this is not in ratios. R1 is equal to 3 R2. R1 is equal to 3 R2 is answer. R1 is equal to R2, R2 is equal to 3 R1, R2 is equal to root 3 R1, right? So let us take the next problem, right? The shape is given. The temperature T dependence of resistivity, resistance as well as resistivity, right? The curves is same for both resistance as well as resistivity of a semiconductor. Semiconductors is represented by, this is increasing, it should not increase. It is decreasing, but linearly decreasing. So this is not right. Yes, this is the correct answer. This is increasing. The shape of the curve. Remember the shape of the curve. Using the shape of the curve, many questions have been asked in the past. The VI characteristics of a non-ohmic device is shown. The region representing negative resistance. Non-ohmic device means what is non-ohmic device? So we are discussing this ohmic devices, non-ohmic devices in the video under the heading Ohm's law, right? You can watch it. Non-ohmic device means the device which is not following or not obeying Ohm's law or non-ohmic device. So semiconductors won't obey it. So non-ohmic device means it is semiconductors, insulators, they want to follow Ohm's law, right? The negative resistance region. We know change in slope or slope is equal to V by I or delta V by I. This is equal to R. How much change voltage makes, how much change current gives. This ratio is R, right? So for R, both should be positive for positive R. But the question is negative resistance, right? So in this region, 0 to A, let me separate the segments, 0 to A to B, B to C, C to D, right? So the question is O to A, B to C, A, B, C, D. So 4 regions they have asked. Let us separate. So here voltage is increasing, current is also increasing, OA. So this is positive. Voltage is increasing, current is increasing. AB also positive. Voltage is increasing, current is increasing. Yes. But here voltage is increasing, current decreasing. Current decreases, I decreases, but V increases. Both should increase for positive region, positive temperature coefficient, for positive resistance. Here I decreases, but V increase. But here both are increasing. So this is positive. So in this region, it is negative. The answer is BC. V positive, but I negative. By increasing the temperature, the specific resistance of a conductor, resistivity or specific resistance of a conductor and a semiconductor. Conductor, for increase in temperature, rho will increase for conductor. Rho will decrease for insulator or semiconductor. This is what we have discussed using the graph also. So T increases, rho must increase for conductor, rho must decrease for insulator. Increases for both. For both means it is wrong answer. Logically you can arrive at the correct answer. Both will not act in unison, right? Uniformly. Increases for both, remain same for both, right? So this is increases as well as decreases. Rho increases, rho decreases. Copper and silicon are silicon is a silicon or germanium are semiconductors. Copper and silicon are cooled from 300 Kelvin to 60 Kelvin. Cooled. Temperature is decreasing. 300 Kelvin to 60 Kelvin. The specific resistance, how it is varying? Decreases in copper but increases in silicon. Increases in copper but decreases in silicon. Increases in both. Decreases in both. This will not be correct. Both will not act uniformly. Decreases in copper. T is decreasing. So for metal, it is directly proportional. Decreases in copper, increases in silicon. This is correct answer. Increases in copper. T is decreasing. You are cooling it. So increases in copper. Wrong answer. This is for both. Yes, definitely wrong answer. Right. So now we have come to the end of the discussion for this class. Temperature dependence of resistivity problems we have solved. The three shapes for different materials, metals, alloys and insulator or semiconductors. We have drawn the graphs, right? Actually what we have done is R is proportional to 1 by n tau. This is the base equation or expression we have taken, and using this only we have discussed in length for different material and draw the graphs, right? Using these graphs and the formula RT is equal to RO of 1 plus alpha delta T. We have solved a few problems, graphs and this formula, right? So thank you viewers for watching this video. Good luck to you all. Yes.